So we will get started. Our next unit is probability. Probability is the likelihood of something happening. It is between 0 and 1, with 1 being certain. This room will be hot today. Probability 1 certain, because it has been boiling hot all week. Okay? Sample space is all possible outcomes, and then a subset or a part of the sample space we would call an event. Oh man, I love this. Oh, wait, you toss a coin, you could get heads or tails. Don't you love it how the unit starts off and you're like, this is the easiest thing in the world, and then at the end it's sort of like, oh my goodness, what have they done to us? Yes. Well, with tossing a coin, yes, there's a possibility that it lands on its side. There's a possibility of flipping it in the air and a bird sees it, eats it, and flies away and never lands. But those probabilities are generally seen as not part of figuring out probabilities. Right? You roll a 6-sided dice. Yes, there is the possibility it could land on its edge. I don't know if I've ever seen that happen, but in an ideal situation, I guess that would be a possibility, but we never list that. We just say the sample space is 1, 2, 3, 4, 5, or 6. Ooh, now you do 2 6-sided dice. How many different sums are possible?
1.
So in this case, and I'm going to use some color coding here, because this is where probability starts to get a little bit interesting. Now when you roll 2 dice, there are 36 possible outcomes depending on what you roll. Some of those outcomes happen more than once. Like you might know that rolling a 7 is more likely than rolling a 2. And that shows up when you look at all 36 possibilities. The 7 happens 6 times, whereas the 2, rolling a 1 and a 1, happens only once. A lot of games, board games, gambling games, are based on dice and using dice. Has anyone ever played the board game Settlers of Catan? Yes? On Settlers of Catan, if you've played that game, each tile has a number associated with it. And now the next time you play that, look at the dots under the number. Okay? There's dots under the number, and the number 6 has 5 dots. The number 5 has 4 dots. The number 4 has 3 dots. The number 3 has 2 dots, and the number 2 has 1 dot. And they're there to tell you, for new people playing the game, which is more likely. So a 6 is a better number because it has 5 dots as compared to a 2, which has 1 dot. And all they're doing is showing you the probability out of 36 for that number being rolled. The theoretical probability of event is based on the following calculation. So theoretically, you have the total number of outcomes in your sample space, and then you take a certain event, like rolling a 7 on a pair of dice, and since that happens 6 times and there's 36 possibility, then the theoretical probability of rolling a 7 is 6 out of 36. But that doesn't mean if I roll the dice 36 times, I will get a 7 exactly 6 times. It doesn't work that way. Same thing when you're flipping a coin, right? 50% chance of flipping heads. Does that mean if I flip it twice that it's impossible to get 2 heads in a row? No. It is quite possible. So some of the probability that we're going to be looking at in this unit that gets a little complicated is like, well, if I roll the dice 8 times, what is the probability I get a 7 twice? What are the chances of that? Whew. And then the probability can get difficult. So we're going to get some difficult probability stuff. So there's our probability of a 7. Means if I rolled it 100 times, I should expect to get a 7 16.67 times. You toss a fair 20-sided dice with faces numbered 1 to 20. Event A is defined as the number obtained is a multiple of 4. I'm sorry, I do not have a 20-sided dice. But I do have a 30-sided dice. Okay? What's the probability of getting that? Well, first of all, you have to figure out how many out of those 20s are multiples of 4. 4, 8, 12, 16, and 20. So then what is the probability? Theoretically, 5 out of 20. 20 possibilities, 5 of them. So if you rolled it 100 times, how many times would you expect to get a multiple of 4? 20 times. You take your probability, you multiply it by the 100 times that you do it, you got a 1 in 4 chance, 25. Experimental probability is when you do an actual experiment to find something. And sometimes you have to do an experiment when the theoretical probability is not known. Now, I have a story of a professor of mathematics at the University of Manitoba wanted to do a study using experimental probability. Because if you flip a regular thumbtack like this, okay, it can land so that if you sit on it, it's not very enjoyable. Or it can land so that if you sit on it, it's probably still not very enjoyable, but not nearly as bad as it could have been. And so there's 2 outcomes. But the reason he wanted to study this is because this is an unknown chance. It's not 50-50 because of the shape. Unlike a coin, which is symmetrical and weighted the right way, hopefully, then you have a 50-50 chance of heads or tails. But when you flip a tack, you don't know what the 50-50 chance is. And so he was telling the story that he got a research grant to do this, and he was able to hire a student. Now, with experimental probability, if you do an experiment thousands upon thousands upon thousands upon thousands of times, the more you do the experiment, the closer the experimental probability should come to the theoretical probability. Okay? If I flip a coin twice, I might get heads twice, and that would mean that the chances of heads is 100% from my experiment. But in theory, it should be 50%. But if you would flip that coin 10,000 times, chances are you won't get perfectly 50 or 5,000 heads and 5,000 tails, but your probability will probably be really close to 50%. And if you did it 1,000,000 times, it would be even closer. Okay? And so this professor got a grant to do experimental probability and was able to hire a student. And that student's 8-hour day job, not sit on them, but flip them and record. Flip them and, do you know how terribly mindless and crazy that would be? You know how long an hour would take if all you could do is flip tacks and write them down? And he said one of the bad things of this student, that the student kind of went a little bit crazy. It's a bad job. So don't take a job which is completely mindless for very long periods of time, because you will go crazy. So here, the experimental probability is the number of times event A occurred over the number of times you did it in total. Okay? And that ratio is your experimental probability. It's also called the relative frequency. How often, what percentage of the time does the event A occur? And then you can use that as an estimate of the theoretical probability. And I wish I remember what the chances are if you flip a coin and have to sit, flip a tack and have to sit on it. What are your chances of pointy side being up? So here's our first example. You toss a fair coin 10 times and you get 7 heads. Experimental probability says 7 out of 10. Your theoretical probability is still 1 out of 2. And by the end of this unit, we'll be able to say stuff like, oh, you flipped a coin 10 times and you got 7 out of 10? Did you know the chances of that are blah? We'll be able to figure out what are the chances of getting 7 out of 10 heads? What are the chances of getting 6 out of 10 heads? The interesting thing is, okay, when you flip a coin twice, your chances of getting 1 head and 1 tail is 50%. But when you flip a coin 10 times, your chances of getting exactly 5 out of 10 being heads is no longer 50%. It goes down because you have so many other possibilities. It's still the most likely of all the things. If you flip a coin 10 times, it's still most likely that you'll get 5 out of 10 being heads, but it's not a 50% chance. So we got it. There's some interesting mathematics coming up. All right, so I got a research grant, and I hired Shemi to just look out the window and look at the cars and what color they are, and write down what he saw. And so then Shemi started setting up a betting ring outside the school window corner. And he was giving odds on what color the next car was going to be. So people could put, 3-to-1 odds on it being red, or 5-to-1 odds on it being yellow, and you could place your bets. And when the next car came by, he paid out money to some students and kept the money of other students, and 2 weeks later was expelled. Estimate the probability of the next car to pass to be red. Well, according to his experiment, there was 138 cars that went by. 45 of them were red. Okay, that reduces to 15 out of 46, which is just under 33%. So there's a 1 in 3 chance, according to his experiment, that the next car will be red. So he would base his, and this is another thing that bets are based on. They look at, okay, if this is the theoretical or experimental probability, what amount of money should people pay and be expected to win so that in the end, the person who's making all the bets makes money? Sorry, there's an S missing there on pass. The next morning, 350 cars pass. Estimate the number of red cars. Well, we take that 15 out of 46, or that 1/3, times it by 350. Yes. Mm-hmm. So what should we do with the 114.1? In this case, since we're estimating, I'd probably just round accordingly. Yeah, instead of rounding up. When do we use rounding up? Well, if it was a more exact kind of calculation and you were saying, how many cans of paint do I need to paint this room? And you calculate that you need 7.2 cans of paint. Well, then if you buy 7, you won't have enough. So that would be a situation where you round up. In this case, this would be one I would just round normally.